Second mean value theorem. State and prove the second mean value theorem for the Riemann Stieltjes integral. Statement: if f is a continuous and alpha is a monotone and also continuous on closed interval ab, then there exists C belongs to closed interval ab such that integral a to b f of d alpha is equal to f of a alpha c minus alpha a plus f of b alpha b minus alpha c. Now proof: since f is a continuous and alpha is a monotonic on closed interval ab, therefore both the integrals a to b f of d alpha and integral a to b alpha d f exist. Let a partition P is a equals to x0 x1 so on xn equals to b be a partition of ab. Choose that t1 t2 and so on tn such that xi minus 1 is less than ti is less than equal to of xi. For all values of I, let t0 is equal to a and tn plus 1 equals to b, so that ti minus 1 is less than equal to of xi minus 1 is less than equal to of ti. Clearly q is equal to a, t0, t1, so on tn plus 1 equals to b, also a partition of closed interval b. Now S P f alpha is equal to sigma I varying from 1 to n f of ti delta alpha I equals to f of t1 alpha x1 minus alpha x0 plus f of t2 alpha x2 minus alpha x1 plus so on plus f of tn alpha xn minus alpha xn minus 1 equals to alpha x1 f of t1 minus alpha x0 f of t1 plus alpha x2 f of t2 minus alpha x1 f of t2 plus so on alpha xn f of tn minus alpha xn minus 1 f of tn, which is equals to minus alpha x0 f of t1 minus alpha x1 f of t2 minus f of t1 minus alpha x2 f of t minus f of t2 so on minus alpha xn minus 1 f of tn minus f of tn minus 1 plus f of tn alpha xn. Adding and subtracting alpha x0 f of t0 plus alpha xn f of tn plus 1, we get S of pf alpha equals to minus alpha x0 f of t1 minus alpha x1 f of t2 minus f of t1 minus alpha x2 f of t3 minus f of t2 minus so on minus alpha xn minus 1 f of tn minus f of tn minus 1 plus f of tn alpha xn plus alpha x0 f of t0 plus alpha xn f of tn plus 1 minus x0 f of t0 minus alpha xn f of tn plus 1 equals to f of tn plus 1 alpha xn minus alpha x0 f of t0 minus alpha x0 f of t1 minus f of t0 minus alpha x1 f of t2 minus f of t1 minus so on minus f of xn minus 1 f of tn minus f of tn minus 1 minus alpha xn f of tn plus 1 minus f of tn equals to f of tn plus 1 alpha xn minus f of t0 alpha x0 minus sigma I varying from 0 to n x alpha xi f of t I plus 1 minus f of ti equals to f of b minus alpha b minus f of a into alpha a minus sigma I varying from 1 to n alpha xi into f of t I plus 1 minus f of ti equals to f of b into alpha b minus f of a into alpha a minus else s of q alpha f. If norms of p is tends to 0, then norms of q tends to 0. So limit norms of p tends to 0 s of pf alpha and limit norms of q tends to 0 s of q alpha f both exist, and consequently limit norms of p tends to 0 s of p alpha equals to integral a to b f of d alpha, and limit norms of q tends to 0 s of q alpha f is equal to integral a to b alpha df. Hence, proceeding the limits when norms of p tends to 0, and we get from 1 integral a to b f of d alpha f of x into alpha x limit a to b minus integral a to b alpha df equation 2. Since f is a continuous on closed interval ab, therefore by first mean value theorem C belongs to closed interval a or b such that integral a to b alpha df is equal to alpha c into f of b minus f of a. Equation 3. Therefore from equation 2 and 3 we get integral a to b f of d alpha integral f of b into f of a alpha b minus f of a into alpha a minus alpha c into f of b minus f of a equals to f of a into alpha c minus alpha a plus f of b into f of alpha b minus alpha c.